Team, welcome back. Let's do an RC circuit problem. Let's look at this problem right here. Now, read the problem. Notice, highlight the things that are important. And for example, to begin charging at initially uncharged capacitor, that's extremely important because that lets us know that it is a charging capacitor. And that is related to the equation. When we write here the physics, it is related to the equation of charge equals capacitance times EMF times 1 minus e to negative t over RC. Okay? Now, it starts at time 0, meaning that initially the capacitor, the voltage across the capacitor, is equal to 0. At time 0, initially it is the voltage across the capacitor is equal to 0, meaning that the charge in the capacitor is also equal to 0. So whatever starts at t equals 0, it will start charging after that, after we close this switch right here. Now, we have that. It's asking us calculate the time at which the potential difference across the resistor is equal to the potential difference across the capacitor. I taught you two ways of doing this, either finding the derivative of charge or using Kirchhoff's loop rule, because you're going to need an understanding of this in order to do this. Two things that I want to make clear to you. A capacitor does not have current going through it. A capacitor does not have current going through it. So you can never solve for like how much current is going through a capacitor. But a resistor does have current going through it. So whenever there is such a thing as solving for current through a resistor, you know that you have to understand that it is the current that is going through this resistor right here. Okay, the current that is going through that resistor. Never about the current going through the capacitor, because there's no such thing as that. Okay? So, it's asking us here to solve for the voltage across the resistor, or equal, like what is the time that it takes that which the voltage across the resistor is equal to the potential difference across the capacitor. We have here voltage across the resistor, and we also have here the voltage across the capacitor. Okay? So, since we have both of them, but we also know that only current passes through one, it's a little bit tricky. So let's start off with Kirchhoff's loop rule. Kirchhoff states that if we have a closed loop, that summation of the change in electric potential across the whole circuit will equal to 0. Okay? So we have that. We also have that the voltage is equal to Q, the overall charge, over the capacitance. This basically means that this is the max charge. What would happen to a capacitor over an infinite amount of time when you're charging that capacitor? What you're going to get is the max charge. The max charge. That is basically what this equation is stating. It is stating that if this is infinite, this time is infinite, this whole thing is going to go to 0. And what you have left is charge equals capacitance times the electromotive force. And we have stated before that the electromotive force is simply the voltage across the circuit. It is the total voltage across the circuit. It is the total voltage across that battery source right here, that battery source. Okay? All right. So we have addressed that. And now let's just finish off by identifying that voltage by substituting Q with this equation. What you have left is the voltage across the capacitor is equal to the EMF times 1 minus e to the negative t over RC. Okay? Remember, once you substitute charge equals capacitance times voltage here, the capacitance will cancel out, and what you have left is this equation right here. So, doing Kirchhoff's, I'm going to erase some of this components, and I'm going to go in a clockwise rotation, and I'm going to name this as my loop. Okay, so doing Kirchhoff's, now let's start solving for the problem. And we have EMF minus the voltage across the resistor minus the voltage across the capacitor is equal to 0. Remember, there is a potential drop every time you pass through it because, as we noted before, current always goes from high to low. And when it comes to the capacitor, since this side right here is positive, it has a high electric potential, and this side right here is negative, it has a low electric potential. So or low electric potential minus high electric potential will give you a negative voltage across the capacitor. Okay, so let us continue solving for this. So we have EMF minus voltage across the resistor, because what we're trying to do is solve for the voltage across the resistor when it is affected by the capacitor. The current is slowed down thanks to the capacitor. The only way that we're able to solve for understanding the voltage across the resistor is by also including the voltage across the capacitor. See how the current is affected by the capacitor itself. So minus EMF times 1 minus e to the negative t over RC. And that all equals to 0. Now, again, you multiply this. You multiply the EMF here minus EMF e to the negative t over RC equals 0. And these two cancel that out. And what you have left is the voltage across the resistor. Oh, sorry, and this is positive right here. This is positive right here. The voltage across the resistor is equal to EMF times e to the negative t over RC. Okay? But it's also, now that we know what the voltage across the resistor is, based on the fact that we know like the capacitor is affecting the current going through that resistor, we also are given that we need to know the potential difference across the resistor is equal to the potential difference across the capacitor. So I'm going to name this step 1. And I'm going to go over here and call this step 2. And step 2 is understanding that the voltage across the capacitor is equal to the voltage across the resistor. So now what I do is simply go here, understanding that the voltage across the resistor can be substituted here, and I also have the voltage across the capacitor, which can be substituted here. That was an awful line. Let me just redo this line. Okay, so we have EMF times 1 minus e to the negative t over RC equals EMF times e to the negative t over RC. Substitute that, EMF minus EMF e to the negative t over RC equals EMF e to the negative t over RC. Notice that EMF, EMF, EMF. These can cancel out because they're all equal to each other, or they have the same on one side. And I could have done it here too, but for some reason I didn't see that. So we have 1 minus e to the negative t over RC equaling e to the negative t over RC. Then you add it together, add these two together, bring one to the other side, and what you have is 1 equals 2 e to the negative t over RC. And then you bring 1 over 2 e to the negative t over RC. Going back here, now you do the natural log because this is the only way that you can get rid of the e. So we have natural log of 1 over 2 equals natural log of e to the negative t over RC. Because there is a natural log of e, what happens is that the e goes away, and what you have left is one natural log of 1 over 2 equals negative t over RC. Then you're solving for time, right? So you go RC, or negative RC, times natural log of 1 over 2 equals time. And this is your answer in terms of algebraic solution. And that will equal to you 0.208 milliseconds. 0.208 milliseconds. So we have a step 1 where you're using Kirchhoff's, and a step 2 when you're actually applying the equation or what it's asking for you in part A. Okay? I hope this problem or this video helps you to solve this problem and understand capacitors, the relationship between capacitors, resistors, the relationship between current in both the resistor and the capacitor. That is all, and have a good night.